Hi, this is lecture 2 for DD211 Math for Designer, and today we are going to learn about set, SET set. This serves as a basic building block in math. Right, the concept itself is not that complicated, but whatever we want to define from now on, they are gonna have to rely on the notation or the wording of set. So this is a good place to start our course. So let's start with a concept. I have this one, which is to have your list from homework. Show them to the class. Like, what's your favorite games? What are the animals you can beat? And what's the other one? I forgot, but yeah, there are three.
Things you are afraid of. Things you are afraid of.
Okay, yeah, that one. There are three, but it was the in-class activity. Yeah, but yeah, the first we're gonna have to, the thing is, no, the question, the reason I asked you to provide me some lists, because when you have lists, lists that have that are in the same category, like animals or games or whatever, then sometimes you have some overlaps between two lists. Maybe that's student A, that's student B. You give me a list of 5 games, maybe 1, 2, 3, 4, 1, 2, 3, 4, and then have something in common. So this is what happened. Hopefully, some of you will have some games in common. But yeah, we are going to describe that behavior or that vocabulary in terms of math today using the definition of set. So let's start from rough. I say rough because you don't want to know the exact definition. That's like language class, not math class, but just a rough definition. It's a box that contains things. A box that contains things. That seems abstract. You have a box. You have things. Maybe you have letter A, you have letter Z, you have letter Y, you have letter J, B. No, this box has 5 letters. So in a sense, this has box. This box has this box. Box has 5 letters. And you can say J is in this box. And say C is not in this box. And so on and so forth. Right, so today we are going to kind of make these statements more formal, so that we can use this kind of statement or this kind of concept in other places as well. And so the concept here is, first we have some of the concept about the box, which is again abstract. It doesn't have to be a physical box, because like for instance, when you provide me a list, like you just list 3 or 5 games, I guess. You just list them out. Like you don't need to necessarily put them in the box. But here the analogy of the box is to give you an idea that they all belong into the same category, the same, in this case, the same set. So that's what the box is for. But the box itself isn't there. Just you can think of it as like an imaginary box. Later you will see that whenever you think about this, you usually draw like a circle or a square around them to indicate that all these objects inside this circle belong to the same group, belong to the same set. So that's what this box is doing here. And then we have the concept about number. This box has 5 letters, this box has 10 letters, this box has no letters, for instance. We can count how many things are there in this box. And lastly, we can talk about things that are inside or not inside the box. this case, whether things is inside the set or not. Right, so whenever we talk about this kind of concept, we don't have to write the whole sentence again, because as you can see, this is long. This thing is pretty long. So we would rather, abbreviate it to something like, J is in S. Sorry. Yeah, J is in S. Come on a little bit. Yeah. This letter J is in the set S, for instance, which is a lot shorter than what we have on the left. So that's a concept, and that's our goal here, to understand what this object or this set is and see what we can do with it. Can we combine things? Can we divide things? Can we mix things up? So yeah, again, this box that contains things, right? And the key concept or the keywords here are, when you think about the box, like you think about things that we have in a collection or a group, or we gather things or a category. There are lots of synonyms that we can use to describe or to visualize the set. Think of it as an abstract box, or if you don't like square box, you can think of them as circles instead, or area. Okay, these things are inside this area, these things are not inside, these things are outside. And then the rest is the question of what we can do with the box once we have them. First of all, we can describe things that are outside or inside. This thing is in this box, this thing is not in this box, and then we can compare two different boxes together, whether this box and that box are the same or not. And then on the third, actually second here, but yeah, we can operate them. What we can do when we have boxes lying around on the floor? Can we add boxes? It's like when we add numbers together. Can we add boxes? Combine, subtract, or other things? And finally, we can. I think yeah, that's the same as here. We can compare two boxes together. This kind of keyword like distinct, distinguish, outstanding, outlier, differentiate. So that's the keywords that hopefully will make you think about a set, or in this case, a box of things. So that's some rough definition. You don't have to memorize each of these words. But now we are hopefully ready. Like once we have things in our mind, we should be ready to start with the definition of set. So first, for this set is box that has things. But then you may ask how can we write them out? So yeah, we have a formal set notation in this case. It's just here. As you can see, the formal definition has first the open and close brackets. Or maybe I should also. Well, I'm not sure I spell this correctly. Bracket. Left and right. And there's kind of like a test whether you do enough math. Is that if you can write this symbol nicely, that means you are not doing math. Because if once you do enough math, or maybe too many math, then you would think that this one is like too difficult to to actually write them up. So if you write it this way, then that means you are maybe good at math, or learn too many math. But anyway, this is the notation we use. You can find that on your keyboard. That's the usual bracket. I'm not sure if you use this in English. Yeah, maybe not. You rarely use this in English or in writing a sentence or a blog or anything. You use this circle bracket, you use a square bracket, But for that, like that has to be like something special. Maybe coding, if you know or if you love coding. But besides that, we don't use them. Besides coding and math. So we have the open one and the closed one, and then we just list things in the box. So for instance, if you think about the numbers, let's say, okay, let's copy that. We have 5 objects or 5 things in this box in an abstract way. Like we can make it more tangent, like not less abstract, like by writing it this way. So it would be all the elements, all the objects inside the box. But then we have to put some kind of separators, so you don't mistake 1 and 2 as 12. So you can see that it's number 1 and number 2. They are 2 separate objects. So we have brackets, we have commas, separate each object, and that's pretty much it. That's all like people actually use for sets. Yeah, that's a set. You can write anything you want inside that. We will learn about types of sets in the fourth part, but for now, that's enough for for us to study the basic definition or the basic operations for sets. And there are a few, actually 3 in this case. There are 3 more symbols that are used a lot. First, we have this empty set. And again, this might be a weird place to introduce that, because usually when you think about box with things, you need things inside the box, of course. Maybe at least a thing inside a box. But if you have nothing inside a box, the box, just empty, just blank. Then the question, this might be like philosophical question, is that how do you represent emptiness? Can you just show me your hand and say, oh, there's nothing on my hand? It'll be too deep. So we have to like kind of make a convention that if you want to represent nothing, it will still be a set. You still need to make you still need to write the brackets, the open and close, but you just put nothing inside. That's right, the open bracket, and then immediately follow it by the closed bracket. And that's a fancy notation, which you don't actually need it. You are fine. You are okay if you write an empty set in this way. But just in case you read some fancy textbook, or you code or you do things that use this notation. But this is called the phi symbol. It's a Greek letter. And you write an O and then you write a line crossing it from top right to bottom left. That represents an empty set, which is kind of a number 0. In this case, you can think of it as like a box, but it has nothing. It's empty, so you cross it out. And that's kind of random reason why we use this phi letter to represent an empty set. So an empty set means it has no element, it has nothing in it. And we might have to mention it somewhere sometimes. But that's the first one. Next one is it's about counting sets. So we said that set, like this set has 1, 2, 3, 4, 5 elements. We can count and we can see how many elements or how many objects are there in this box. And so we represent the size or the number of objects by this notation, which is just 2 straight lines around the set A. Oh yeah, by the way, that's the name of the set. I think it's somewhere. Yeah, of the set. You can use any letter you want, but usually, conventionally, maybe use capital letters to represent sets. Maybe ST, no, maybe XYZ. So as long as they are capital letters, then you should almost always think of them as set. So that's the name of the set. And then we have this like this straight lines on left and right. And that means it counts the number of elements. And it can be 0. If you count the size of the empty set, you can write it in this way, and that will be 0. Which if you take a look at this for a moment, it looks weird, isn't it? This looks pretty weird. If you don't know math at all, or even like if even this is the first time you learn about set, then it looks like foreign language. But yeah, it is what it is. And it is empty set, and this notation counts how many elements or how many objects are there in the set. Since there is nothing there, so the number is 0. In this case, the size of that set is 0. And then it can be a positive integer. Like we are counting things, they have to be integers. So it can be 1, 2, 3, 4, 5, and so on. Like if I ask you how many elements are there in the set, in this set, you would say there are 2 elements because that's 1, that's 2. If you can count, then you can easily say how many elements there are. Or it can be infinite. Some sets or some box has lots of elements that you cannot count. Like for instance, you can have a set of numbers. That's pretty abstract. Lots of numbers. Oh, someone requests to join. But if you think about sets of numbers, or even like sets of, let me add the word counting then. You want to see the set of counting numbers, then the number is infinite. And we represent that as infinity. And it can be uncountable. And you might ask, wait, aren't they the same thing? Maybe let's think about it for a second. Right? The set can be infinite or uncountable. I know it seems like there's something weird going on here. Right? It can be infinite, or it can be like kind of more than infinite. Yeah, that's a fun topic to study on later days, but for now, you can just ignore this part. But in theory, it can be that, but all we get here are, 0, positive, or infinite that we can count. So that's the size, and that's the notation. And lastly, we have this notation. This is pretty much like the reason why we study set, because this saves you lots of inks, lots of writing energy. Like whenever you see this notation, in this case it is x, and then this e, a color e, and then the letter a. Like this thing reads as x, like the left part, is an element, or is in. And that's this symbol is in the set A. Like something is an element of the set A, and we abbreviate it to just x and this new notation and then A. So these are the basic notations we need for now. The empty set, the size, and the element, or I think the word they call is the membership. It seems like something you apply for gyms or anywhere else. So that's all for the basic, for the start. So let's see if we can apply that to business. So the example is asking you to express the following sets. So there are 1, 2, 3, 4 examples, like using set notation and also file size. How large each of those things are. The first is a set of letters in English alphabet. Then we have set of planets in the solar system. Then we have set of odd positive integers less than 10. I think someone's brain stops working at this statement, but yeah, we'll see if and also the set of integers whose square ends with 3. Weird, right? Yeah, let's start from the top then. So if you want to write the set of letters in English alphabet, you would, first give it a name. Let's say A. Or maybe alphabet. You can write as anything you want. Right, then we write it in the set notation. So we have the close open bracket and then the close curly bracket. And then we should simply list them all. A, B, C, D, E, F, G, H, I, J, K, L, not P. Sing along if you can. H, I, J, K, P. U, R, S, T, U, V, W, X, Y, Z, and I guess that's all. Let me know if you can find something else. But yeah, I think that's pretty much it. But that's a huge set. And if you ask how many elements are there, or what's the size of this set, you would just like you just write the left and right vertical lines. And that should give you hopefully the same number, which is 26. The size of the English alphabet, the basic ones, 26. So that's it. Right, and before we move on, there are 2 comments here. Like first, it looks, like waste of spaces, because if we use the same language, then you don't need to write them all. Like sometimes you can, if it is obvious what the pattern is, you can sort of abbreviate it. In this case, like you can write ABC and then comma and then dot and then comma and then Z. So we can see that, okay, there are A, B, C, and then Z, and then this dot represents that there are more. It's telling you that there are more there. I don't want to write them all. You can find them out if you have time, for instance. So this one is acceptable. As long as the pattern is obvious. Like for instance, if you write, A, C, F, and then dot, and then Y, then nobody knows what you mean by that. Can you find any pattern between these 4 letters? I can't. Let me know if you can. It's gonna be too random. So you can do that if there's an easy way to fill in the blank. So that's one comment. And the next comment is maybe I should also write down there is that you can, once you have this set, now you can write, okay, J is in the set of alphabet, or X is the set of alphabet. Oh, that's missing an L. 0 is not, I should also add that notation. 0 is not inside the set of alphabet. It's gonna save you some spaces when you talk about these concepts. Like that something is an alphabet. Something is a letter in the alphabet means something is inside the set of this alphabet. There is a letter but you can see this one is a lot shorter. It could even be shorter if you use just a single letter to represent the name of the set. That's mostly the main application of the set. Oh yeah, and this one I forgot to mention that if something can be in the set, then you can say that something is not in the set by writing it as the same, using the same symbol with the dash that says it's not, just like equals and not equals. a member and not a member. So that's the first example. Then let's keep the next one. Oh, let's go over them all then. Right, then the next one is we are running out of spaces. The next one says you have to list the planets in the solar system. So since it's stars, let's say the name of the set is S. Solar system or stars or whatever. Then you're gonna have to list them all. Like, what are the planets then? There's gonna be like Mars, Jupiter. Oh, by the way, it's not in the order because I can't remember. So forgive me on the lack of solar system knowledge, orbital knowledge, and so on and so forth. So that would be the set. Right? I think the lecture has all the names. Maybe I should cheat and take a look. Oh, my bad. I haven't uploaded. My bad. 10 seconds. Yeah, I knew I was missing something, but will be uploaded soon. Okay, yeah, is this now uploaded? Sorry about that. So now you can see what are the planets, what the planets are in the solar system. Yeah, Earth, Jupiter, Neptune, Mars, Uranus, Saturn, Venus, Mercury. And again, this might be disputable. Some of you still remember Pluto dearly in your heart. Some of you use the updated version that says Pluto is not our family. It is not welcome to the solar system. But regardless, though, let's suppose that they are not, then that means the size of the set is only 8 without the Pluto. So that's the second one. Oh yeah, maybe I should. Yeah, A, B, C, D. And that's A, the alphabet. B is the star. So for C, we have the set of odd positive integers less than 10. Sometimes, this kind of it's very wordy. You have to know odd, the word odd, positive integers and less than 10. But there's only one way to describe that. But if you can write as a set, you just write it once and use it everywhere. So let's say that's the name of the set is E, so it's next to S. And here you can list them all. So we need a positive integers, so it's 1, 2, 3, 4, 5, and so on. But it's less than 10, so it's between 1 and 10. Only the integers or the whole numbers between 1 and 10. And it has to be odd. It has to be an odd number, so this set only has 1, 3, 5, 7, and 9. So this set of odd positive integers less than 10 has its 5 elements. And I'm sure you're gonna prefer this version to that version. Yeah, but sometimes you have to, write it out. And if I ask you to find the size of the set, you will say 5. There are 5 things, there are 5 objects, there are 5 elements inside this set. And so that's C. And lastly, that's a D. So ST, let's say, W then. So we are looking for the set of integers whose square ends with 3. Again, lots of math word. And so what it means is that if you have an integer, if you have any numbers, then if you have any numbers, you can find a square, right? I give you one, maybe I should write it here. And if I give you a number, you can find a square, right? One square is 1. If I give you 2, you can find the square of it, which is 2 square, which is 4. give you a three. You can find 3 square, which is 9. For 4, we have 4 square, which is 16. 5, we have 5 square, which is 25, and so on. And so the question is, like, what are the integers or the whole numbers whose square ends with the digit 3? It ends with the digit 3. So we look at those numbers and see what are those ending digits. So we have 1, 4, 9, 6, 5. So far we haven't found anything yet. Maybe you believe that if you spend enough time you can find them eventually. But as you would what you have guessed, x squared is 64, 9 squared is 81. You still can't find them. You can't find anything whose square ends with the letter 3. With the digit 3. So now it's up to you whether you want to continue fighting like an explorer, or just stop and give up and live and cry. But anyway, nonetheless, we can prove that that's a math fact. That if you square a number, you would always end with digit 0, in case you get 0. Or 1, you have 0, 1, 4, 9, 6, or 5. There are only 6 possible ending digits. And 3 is not in the list. So of course there's nothing here. But that doesn't mean the set doesn't exist. No, the set exists. Like that's a set. It just happens that the set we want doesn't have anything inside. Nothing on earth satisfy the requirement to be in the set. Just like you may want to find a person who is, I don't know, rich but broke. Is there such thing? And sometimes there are too many requirements that nothing works, nothing satisfies them all. And so the set exists. It just has nothing inside. And in this case, of course, since it is the empty set, we say that the number of elements is 0. And so that's how you write a set, express a set from a sentence or statement into a mathematical term. Do some math with it. So that's the basic notation. And next one we have some extra notations. So here we talk about set itself, and things or objects or elements inside the set. Next we want to compare sets. Like we have 2 different sets, and we want to see if we can say anything meaningful about it. So we have there are 3 notations there. And if we have first this notation, and then that which looks similar and over. Let me say that we are not going to use this in this course because personally I find them confusing. But let's start from here. Like we have a set A, we have a set B. And then we can say that A is a subset of B. Sub means small or inside or part of. And here the concept of the subset is that sometimes you have a box. It has 1, 2, 3. Then you have another box or another set that only has 1 and 2. So in this case, you can say, oh, they look similar, except this one has more things. The set on the left has more things, has more objects than the one on the right. So in this sense, they are not only larger, but they also contain everything. It's like they contain a copy of the smaller set. So in this case, we compare these 2 sets and say that here the smaller one is a set, it is a smaller set, so it's a subset, as the definition suggests. And it is a subset only when every element of the smaller set is also an element of the bigger set. What this means is that sometimes we have sets like let's say the set B is 1, 2, 3 as before. And then the set Z is 1 and 4. 1 and 4. Let's say there are 2 elements. Oh, actually, we have the notation already, so let's just use it. B is a set of, B is the set that consists of elements 1, 2, and 3. And then A is the set 1. So here is kind of in the sense that A is smaller. If you compare them by size, you could see that, oh, there are only 2 things in C, but there are 2 things in B. And so A is smaller. But even though they are smaller, like they cannot be compared. Because you can argue that 4 is larger than everything inside B, so A should be larger. I don't know, maybe. Again, that's kind of the philosophical question you're gonna have to ask. If you have like more quality people, but smaller number of people, is it better or worse? And so in this kind of comparison would be considered as meaningless in math. Like we cannot compare. We can't compare A and B. If the elements don't match. We can only compare them if the elements match. In this case, we can find one from the smaller set, like inside the larger set. We can also find 2 in the larger set. So here, now we can say something that, oh, A is actually smaller than B. So that's the concept of the subset. And we use this notation because actually you might want to use that, like to represent that the set A is smaller, quote unquote, smaller than B. But again, they are not actually smaller. Right, because small doesn't make sense in set sometimes. So we just adjust that and use the curly version of the less than instead. But they kind of give you the same concept. And then we have to set B. Okay, so to say that A is inside B. And we have this line. Like this serves the same purpose as the less and less than or equals to. Like we write a line below the less than symbol to say that they may be less than or equal. Like it is possible to be equal, to be the same. So we use the same notation here instead. We say A is a subset, or R equals to B. That's the origin of that. And sometimes, just as a note, sometimes you see this notation. In this case, you say that A is a subset of B, but they are not equal to each other. What that means, it has to be a proper subset, or you can say strictly smaller. You should not use a small strict subset. Big subset. But again, that's kind of like confusing. And also sometimes some people use that as the same as that notation. Like some people use this to mean that there is a subset of B or the same as B. And so we just throw that away in the bin and don't use it at all. So I'm gonna just stick with that. And lastly, we can say they are equal if if everything matches, if they are the same exact copy. And one thing to note here is if you read the definition, it says that if all elements in A and B match, right? It doesn't say anything about the order. For instance, if I write A as 1, 2, 3, and I write B as 3, 1, and 2, in this case, I still treat these two sets as equal. Because this definition only care about the elements, like not the order. They are the same. But that means you can switch things around. That is set. Oh yeah, before we take a break, let's take a look at some quick example. Okay, so here we want to that there are 4 sets. Like there are sets of numbers, and here we want to see if we can compare some of these sets. Like some of these sets may be a subset of another. And so let's see if we can compare some of these sets. First, A is a set of even numbers. So sometimes you might have to write them out before you can imagine what they are. In this case, the set of even numbers are 0, 2, 4, 6, and so on. So these are even. 0 is also an even number. Because if you go to the definition, right, an even number is a number that can be split into 2, where they are both number integers. You can split 4 into 2 integers, 2 whole numbers. You can split 2 into 2 whole numbers, like 1 and 1. You can split 0 into 2 numbers, 0 and 0. It's kind of weird, but that's how we define even. And so these are numbers, and you may notice that there are lots of spaces on the left. Yeah, because in this case we also consider the negative numbers. Just numbers, -6, -4, -2, and so on. So we have a set A. Oh, and it needs to also continue to infinity. So let me rewrite that. A equals ... comma, -6, -2, and so on. Now B is a set of odd numbers, so just write the rest. Would be represented in this way. So that's A, that's B. Then for C, now he had to do some math. The set of numbers whose last digit is 0. You have to think about numbers and see the digits. So you can think of 0. The last digit of 0 is 0. Then we have 10, 20, 30, and so on. So those are positive or non-negative numbers that end with 0. And then by this definition, you also have -10, -20, and so on and so forth. So you can list some of them out to see how they look like. And finally, the set D. The set of numbers divisible by 2. Again, you have to know some math, have some basic math, and you will notice that, actually, there are actually another definition for an even number. And here, if you know the definition of even number and divisible, you can recognize immediately that the set A and D are just the same set. They are just described in 2 different ways. So in this case, we can say that A and D are the same. A equals to D. And what else we can say about, well, for B, you can say, they have all the odd numbers, and those odd numbers don't appear anywhere else. So B is, not in, B is not related to anything. For C, we have 0, 10, 20, 30, and so on. And then you have to know some basic math that, if it ends with 0, then that means it is also divisible by 2. So if it's 10, then you can divide it by 2 to get 5. If it's 20, you can divide it by 2 to get 10, and so on and so forth. So by the definition, like this set C, it has the elements that are also in D. We can see that everything inside the set C is somewhere inside the set D. And by the definition. So here we can write that C is a subset. Oh, my bad. I shouldn't use that. With that, C is a subset of D. It is smaller. It has everything. Or D has everything that C has. Everything that is divisible by everything that whose last digit is 0 is also divisible by 2. that's what we have. And oh, lastly, yeah, since D and A are the same, we can also say that C is a subset of A. There's some relationship between some sets. So that's the end of the first section.